Good afternoon, everyone. You are currently in Palace One, and the name of this talk is Multiplex Wired Attack Surfaces. I'm going to turn you over to your presenter. Thank you.
Thanks. I'm Michael Osman of Great Scott Gadgets. This is Kyle Osborne.
Hi. I'm Kyle Osborne of a company.
Thanks for coming to our talk. We think it's a lot of fun, and we hope you will too. So this is the teaser. This is like why you should not get up and leave our talk. You've locked your Android device. You've disabled debugging, and if you followed causes for it, am I doing poorly?
He has a.
Okay. So you've disabled debugging, ADB. Like you go into your phone and you select USB debugging off. Somebody like a customs officer could still grab your device, plug something into your USB port, and get a shell. And we're going to show you how that can happen. The stuff we're talking about is primarily stuff that's actually public knowledge to some extent. It's a lot of the stuff that we are showing is stuff that we have found other people talking about on the XDA developers forum. So people who are modding phones know some of this, but people in the security community we've found aren't very familiar with this stuff. And so we're trying to raise awareness in the security community and expose some interesting interfaces as attack surfaces and think of them as attack surfaces and what can happen. Since electronic connectors have existed, they've been repurposed. I've seen serial interfaces implemented over connectors that were intended for power connected to over serial interfaces, all kinds of crazy things. One example that you're probably all familiar with is power over Ethernet. You have an Ethernet cable that carries data, and why not run a little bit of power over it at the same time? And that's something that was done, kind of after the fact. After people were already using these twisted pair Ethernet cables, people started repurposing them and adding in this extra function of power. Another example that everyone's familiar with is DSL. You have a telephone line to your house. You run voice over it, but it's possible to carry data multiplexed with the voice over the same pair of wires. And it creates an entirely new connection over the same physical medium. Another interesting example that I like to point out is the iPod Shuffle. The iPod Shuffle, I think the first one, and certainly later ones, have USB implemented over the headphone jack. And so if you buy a Shuffle, it comes with a special USB cable that has a USB-A connector on one end, and it has TRRS, a four-conductor audio plug on the other end. So it actually lets you plug USB straight into this audio port, which is also used for audio. So this is the first example that I know of. This and some other portable music devices, MP3 players, do this kind of thing, where they actually implement multiple different technologies, in this case, audio and USB, over the same connector. And they have some kind of a detection circuit in there that figures out what's been plugged into it and switches the function from one type of interface to another, even over the same connector. And a user of such devices doesn't necessarily know all of the multiplex functions that might exist on a port. You might have an MP3 player and you might use headphones with it and never realize that somebody could connect to your headphone jack and get a data connection. Should I turn off my lavalier? Would that help? Is that better? All right. So a typical USB device, for example, And USB is what we've been focusing on primarily with this work. A typical USB device has something called a USB device controller, and it's an integrated circuit that is what actually runs the USB connection. So you'll have a connector on a device, and then there's a USB device controller attached to the connector with a few traces on the printed circuit board. And then it talks to some CPU. And that CPU may be actually in the same integrated package. We see a lot of microcontrollers that have an integrated USB device controller. So those two things might actually be one IC. But typically you'll see that device controller connected directly to the USB connector. So if you plug into the USB connector, you're talking to the device controller. Now, mobile phones and tablets in recent years have started to do things a little bit differently. There's a CPU, and it has a USB device controller, but it does not directly connect to the USB connector. In between the two is a multiplexer IC, an integrated circuit that detects what type of thing is plugged into the connector and redirects the connection or switches it between the USB device controller and various other functions. And we think this is very interesting as a potential attack surface. We've seen some interesting attacks on USB hosts in recent years, like Travis Goodspeed's Face Dancer project has exposed a lot of interesting stuff. So you can plug into a device and attack its USB stack. That's an interesting attack surface on its own. But we've discovered that there is a much greater attack surface. USB is just one of the functions that you can reach from that USB port. And we're finding other things. In particular, the multiplex functions that are handled by that multiplexer IC that are commonly seen. One is USB on the go, which is a way for it to automatically switch between host mode and device mode. And another is audio, where the USB car kit standard actually allows the USB connector to carry audio data in an analog form. Another is, and this is the stuff we're most interested in, is that we see a lot of debug and programming interfaces accessible through the USB connector and through that multiplexer IC. This is a diagram from a data sheet from one of those multiplexer ICs. And you can see that on the right-hand side, there's the connection to the USB port, a micro USB connector. And on the left-hand side, there are connections to various back-end things within a phone, for example. One says HS USB, that's the high-speed USB connector. So that's what you'd expect to connect to when you plug into a USB port. But there are other things that it can switch to. It can switch to an audio codec. It can switch to a UART with receive and transmit pins. And it also has control and an interface to talk to a baseband processor or some kind of a microcontroller that controls this chip and also interrogates this chip to find out what it thinks what devices are connected at a particular time. So how do these things detect a device? Like, how do they determine what device is connected? They do it using a technique that's generally referred to as accessory detection by the chip vendors. So if you're searching for these multiplexer ICs, that's a key word that you want to look for, is accessory detection. A USB port, like the big A connectors that are on your computers, your desktops, your laptops, have 4 pins. But the newer micro USB connectors and mini USB connectors have 5 pins. That 5th pin is the ID pin. And it's a pin whose purpose was originally intended for USB on the go. You connect in the plug of a cable. If you're making a cable, you connect the ID pin to ground if you want that cable to tell that device you're plugging it into to switch into host mode. Or you leave the ID pin unconnected and plug that in, and the device assumes that it's in device mode. And that's the crudest form of accessory detection. And people have extended that, or manufacturers have extended that over time, where they start detecting different resistances between ID and ground. And so this is a list of all the different resistances that can be detected by that particular multiplexer IC that I showed earlier. You'll notice it's quite a large list. There are all these different fixed resistor values that you can just attach between the ID pin and the ground pin on a USB connector and convince it that such and such a device is connected. And I'll just zoom in a little bit on a section that's interesting to us. There are a number of TTY converters, UART, factory mode, boot modes. These things are debug interfaces and programming interfaces for like loading code onto a phone or debugging that phone in some way. And in particular, we found a lot of phones, especially Samsung phones, have this UART cable line where it's for a 150 kilo ohm resistor. If you just connect a 150 kilo ohm resistor, it's like a 1 cent part, in between the ID and the ground, it connects your USB or the USB connector on your target device into a TTY UART that you can talk to. So what's a UART? It's a serial port. There was a talk earlier today that was like a really good primer to UARTs, I think. Did anybody go to that? That's exactly what we have here. And it's a TTY UART, TTL UART is what I mean to be saying, which we've kind of abused the term TTL over the years, but it means that it's a serial port that operates at logic levels. So like voltages from 0 to whatever the operating voltage is of the chip you're talking to. So 0 to 3.3 volts, 0 to 1.8 volts, might be 0 to 5 volts, as opposed to RS-232, which is basically the same protocol, but with much wider voltage swings that go to like a really low minus voltage as much as minus 15 volts and positive 15 volts. So a big voltage swing of as much as like 30 volts. TTL is the same, the TTL UART is the same protocol basically, except implemented over a much narrower voltage range and operating at familiar baud rates if you're old enough to remember modems. So here's what we do to interrogate one of these things. We get a USB connector, like a micro USB plug. We connect a fixed resistor of 150 kilo ohms between the ID pin and ground, and then we connect the USB data lines, the two lines, to the transmit and receive lines on our own TTL UART. That's all we do to start talking to these things. So let's build one of these. Here we have a little breakout board on the left, which is a micro USB connector with you can see that blue resistor soldered in there. And then we literally just have three pieces of wire and a resistor is all we have to solder. And we connect this thing to what's on the right, FTDI UART, that breakout board. And the FTDI UARTs are super common. Everybody uses them in the embedded electronics world. And it's a readily available chip, and it's easy to find breakout boards like this. These are from SparkFun, but you can find similar things from a lot of other vendors. So it gives us a way to plug in. You'll see that there's a mini USB connector on that FTDI board. We plug that FTDI board into our host computer. And then we plug the USB micro plug on the other side into the target device. And then we're able to communicate using that UART with whatever UART is connected inside the target device. Don't be confused by the fact that we're using USB to talk to the FTDI. We're not using USB to talk to the target device. We're doing something else over the USB connector. And what we found on the first device we tried this on was that we hit enter a couple of times and boom, we get the FIQ debugger, which gives us some interesting things we can do on a phone. The FIQ debugger is something that is part of the kernel in the Android kernel. You want to talk about it?
Yeah, because I mean, I better do something than just look pretty up here. No, I'm really loud. So the FIQ debugger is actually a kernel module that I don't really know a whole lot about it. It's used way back. Like if you search Google, you can find old applications or old hardware uses for it where people had it in radios or whatever, and to debug it and to access it, they had this this module which would reveal a TTY and a few other pieces of data and debugging information. And this was actually included in Android. I guess, I mean, for obvious reasons in that you need to have a method to access, you know, the sensitive information, or not sensitive information, debug information and kernel logs and all that. Because if you have a kernel panic and you can't use the device as USB connector because that's part of the kernel and that's a USB driver, or some other method to access it is unavailable, or you know, ADB is an application, a service that runs, and if the kernel freaks out, you can't access it. So they have this, which actually will provide plenty of more information before everything kind of just goes kaput. And it also allows you to access other things. You could potentially push updates to it, or write firmware with it, and other types of things. A kernel debugger is included with this if compiled with it. We haven't seen any, you know, any phone or, oh, you have seen one. So he has seen one that does have kernel GDB enabled on it, which would allow you to do kernel debugging, which would obviously make it, you know, you have root or do whatever you want immediately. But it does provide you lots of information about the phone regardless.
So let's give it a try. We're going to switch over to Cos's computer here.
Yeah, we are.
Yeah.
Computers, how do they work?
And pray to the demo gods.
I did not sacrifice enough children. I mean, that's not funny. All right, let's see. So I'm having this hard time with Ubuntu or with Windows, where it does not like to do split screens.
Yeah, so he's having to look at that screen on Edge to see what he's doing.
Sort of. I enabled VNC in my virtual machine, so you're all watching VNC to a virtual machine that's very local to my machine. Sorry, very hacky, I know. All right. So, as Osmond said, we do have this device here, which we can just go ahead and take in this Galaxy Nexus right here. Unfortunately, I can't show you the screen because this is one of the devices that I kind of destroyed on accident, as I do. But we go ahead and plug it in, and then we can mount this as or connect to it as a serial device. So I'm just going to use screen. Can you guys see that? Is that big enough up there? Oh, that's a bad color, isn't it? Let's see if I can. Sorry, I'm really bad at giving presentations. I should just like stop. Just joking. Great. Okay, cool. That's a little better. Cool. So we have this white screen, hit enter a few times, and we see a debug interface. And this is actually running on the device. Originally, I thought this was like part of the firmware, like part of the multiplexer chip or something. But it turns out it is actually part of the kernel. So you can look at the source code. It's pretty nice. It's pretty easy. It would also be really cool to find like a buffer overflow here too, because this is actually talking directly to the kernel and kernel space. This is not a process running, but it is cool. So we can see all sorts of interesting things like PC status or registry dump related stuff, few random bits of data. You can actually pull down like stack traces and get some stack trace information. I haven't actually found anything particularly useful with this, but you know, others might.
So in most cases, we found that the FIQ debugger that's installed in the firmware on an Android device is, it can be absent sometimes or disabled. It can also be compiled in a read-only mode, or it can be compiled in a read-write mode. And in most cases, we found it enabled in a read-only mode.
Right. So, but even in read-only mode, you're still able to access, basically read all the information. So some of like the really good stuff, interesting stuff would be the K-message or K-message, where you get kernel logs and that sort of data, which takes kind of a while because it's serial. But yeah, so you can pull that sort of stuff down. Now, funny thing is with CyanogenMod, for a while, if you typed in the wrong code, or if you typed in the right code, it would log that code, your pin, to the kernel logs. So you would actually be able to pull the code, the pin from the kernel logs like this. So that would be an attack vector. But yeah, theoretically, you could find some sensitive information here. But again, it is only read-only. It's not the most impressive thing in the world.
Except
There's this cool little command here called console. Switch to terminal console. Anybody want to guess what that does? I'm just joking. So it does actually drop you into a console mode, which spits out lots and lots of kernel freaking annoying stuff. There we go. So now we're actually running as shell user on the device on the phone. And I think we should have mentioned there are some stipulations to this. This device, wow, that got a lot louder. I suck at this. This device specifically is running a custom ROM. I want to like call us crazy, but there were 5 of us around a table with someone else that showed us. We have seen it on.
I've seen this on some, off-the-shelf phones with vendor-provided firmware.
Yeah, so we have seen this with like stock software, not Google stock software. Google actually disables this in their Nexus builds, but we have seen it in stock builds of regular vendors. The problem is it varies from vendor to vendor. It varies from provider of that ROM. So Verizon is going to be different than AT&T, and it also varies from the I believe it varies from the actual model number of the devices, because the S3 has at least 5 different model numbers for the same phone. And unfortunately, finding all of those phones and having them readily available to test everything is not super easy, which is why we share information. So maybe someone that does can play around with it. But in this instance, we're actually running a custom ROM. ADB is, in fact, disabled on this device, and we have nothing to do with ADB right now. But you'll notice we are a little bit limited. When you run ADB, you run as the user shell, which is a fairly limited user. You can't access the data partition, which contains all the SQLite databases and all the other stuff, the fun stuff. You can install applications, you can pull down logs, you can make configuration changes of the phone if you know how to, and that is available. And a lot of the reason you can do that, like in this instance, we can't even access the SD card on this device. It'll give us a permission denied because we don't actually have the permission to read the card. So when you go in as ADB, it actually drops you, it does a set GUID, a group ID for a bunch of different groups. When you go in this method, you only have that single group, which is shell and log. So you're pretty limited in what you can do in some instances.
So it'd be nice to be able to elevate privileges somehow. Right now, we have very restricted access as this shell user without the same group permissions that you would have if you had ADB connectivity.
Yeah, that's over.
All right. So all of these debug interfaces were put there by somebody intentionally. Like they're intended to be used by somebody. And you can actually find commercial test jigs that are designed to provide connectivity to some of these interfaces. For example, the Samsung Anyway S102 is one that we have up here. It's this blue box, and it supports a whole bunch of Samsung phones and tablets. I mean, going back to like a lot of non-smartphones, feature phones, all the newer smartphones and tablets from Samsung are supported on this device. And it has these predecessors, the S100, the S101. We just have the latest one here. It looks like this, and it's this blue box, like 3 or 4 inches square. And it turns out we can just buy one online. So the only hard thing about buying one of these is knowing the model number to buy. because like the only authorized seller of these in the United States doesn't really list them with very much information other than this model number GH99-36900B. So we've done the hard part for you. There you go. It costs $100 or so. And then you need a cable to connect it to like the USB port on a target device or whatever kind of connector the target device you want has. And then you need some like a power supply for it. So for a total of $200 or a little less, you can get this whole setup and have the same tool that whoever is programming these devices in the factories or at the mobile carrier or wherever they do these things. This is probably the same equipment they use to program to load code onto them. There's this test pack connector, and this is a DB25 connector from which this thing connects to the target device. So that's why you have to have a special cable to go with it. In our case, we're mostly using devices that have a USB cable or USB connector. So you get from Samsung, you get this cable that's DB25 on one end and USB on the other end. And they have a whole bunch of these different pigtail cables for all the different connectors that are on their various devices. The other side of this device has these UART ports. So you can connect, here you can connect, I think, a RS-232 port from a PC, and this kind of gives you a path from your RS-232 connection through the thing into the phone. And then there are the solution dial and the function dip switches. And these are kind of confusing. We haven't found any comprehensive documentation for this at all. But there's this, I don't know, you can kind of see on the top of the device like this table of functions and solutions. And we understand some of them, but not all of them, probably because this device supports so many more target devices than we've actually tried.
Yeah, and one of the largest problems with this device is it's not publicly documented. Like, we can't find a whole lot of information on this. The only reason that we kind of figured out how to do a few things is I was searching a lot online one day. I was trying tons of different queries in Google and all this other stuff, and I came across some random PDF that actually showed this device with an S3 or a Galaxy Nexus or one of the phones, and it actually kind of detailed what to do. Plug the phone in, plug in the power adapter, plug it into your device, connect to it over serial with these connections, flip these switches in this way, and then you're set. You can go. You can do all sorts of fun stuff. Unfortunately, that was on like some random FTP site or FTP with anonymous access hosted by a Russian telecom service. So I pulled that down and it was a PDF, so I opened it in a VM just in case because it is Russia. But it's really hard to find. Actually, the easiest way to find this data is you look at the bottom of these sheets and you just copy and paste at the very bottom, internal Samsung, confidential, and
those are great Google search terms.
Yeah, and you can find a lot of information about a lot of different devices. But it's really hard to find. We can't find anything conclusive. And I believe when he ordered it, didn't they call you and they were or they emailed you?
Well, I tried to order since I happened to find in their website a service manual, like a complete service manual for one of the phones we wanted to attack. I said, I'll just order that too. It's like an extra $30, but hey, if I have a whole service manual for this modern phone, that'd be fun to have. And then they ended up delaying my order because they couldn't fulfill that part of it. So that sucked.
Yeah.
But the inside of this device is not too interesting. There's a PIC microcontroller that controls everything. There's a bunch of power switching stuff because a big part of what this device has to do apparently is charge or power a wide variety of different target devices that are plugged into it. So a lot of the surface area in this thing, a lot of the volume of this device is just taken up with power electronics. And then there's this kind of grid above, just above that that long DIP package microcontroller. There's kind of a grid of surface mount parts that includes a bunch of fixed resistors. And you can you can't read it from there, but with my magnifying glass, I could read the values off those resistors, and hey, sure enough, there were several values that corresponded to the table of values that are commonly used for those multiplexer ICs. Interestingly, 150 kiloohm is not in this. And although we have connected to some interesting services available or ports available, interfaces available on target devices with the Anyway, we have not connected to the same one that we got over our little home-built FTDI port, except for once, which we think was an anomaly.
Yeah,
the device wasn't behaving properly.
And the annoying thing is, like, because it's not documented, you kind of sit there and you just go, all right, solution 1, dip switch 1, nothing happened. All right, number 2, nothing happened. Number 3, nothing happened. And the annoying thing also is there you can combine them too. So you can have like number 3 and number 7, and it takes forever. It's really hard to find, which is why it's way easier just to have a 150 resistor sitting around and do it that way.
Yeah. So here's actually a better shot of the table. It's kind of a confusing table because the numbers on the left-hand side it looks like the solution table has something to do with the function table, and they really don't. They're sort of two different tables that are both borrowing the same list of numbers. So what we're really interested in and what we've had success with is that 150 kilo ohm UART cable line. But what the Anyway gets us are mostly those modes that are factory mode, boot, off, and you can kind of see it here on the function on the right-hand side. You can see there's a couple of lines where they have like MUSB and like whether it's going to boot on or off, ID boot. Those are related to these lines that are factory mode, and they seem to be primarily used for loading code onto the device. So we're the shell user when we get the console from the FIQ debugger, and it's like Kaz mentioned earlier, it's the same user as ADB runs, but without all the same group permissions. So it would be really nice to be able to elevate privilege somehow. And we found some ways to do that, but the most obvious way was that we could like write to some files, and maybe we could install an APK and actually like load our own code to run on the device. And this turned out to be super hard. Have you ever tried delivering a payload over a slow, unreliable serial connection that can only handle 31 input bytes at a time and spits out all kinds of random kernel debug messages at you at any given moment? It's really, really difficult.
Yeah, I spent hours and hours and hours. I spent right before a presentation we did previously, I probably spent 4 hours trying to figure out how to transmit data at a consistent rate without losing random bytes. Like every once in a while, it would just be like, all right, I'm done. Like I don't want to send anymore. And then it would go to the next line and send more. So we'd always end up with these broken payloads that would be missing like, less than like 1% of the data, but we just could not figure out a way to properly do it.
It was super annoying.
And we got it. I tried hard using so a lot of the ADB stuff I did previously. I've been looking at how Android install what applications can do and all sorts of stuff. So one of the attack vectors that I had with my previous projects was the ability to disable the lock screen, which would be great because then you can plug it in, push your payload over, disable the lock screen, and then do whatever you want. And you can make that really small in an APK. You can make an APK that's about 4.5 kilobytes, and that includes the whole zip architecture. That includes compiled Java, some other resources. I mean, in reality, it's only like 3 lines of code. But everything, once you do it, it's freaking ridiculous. So I actually had to take the 3 lines of code, compile it. It turned out to be 17 kilobytes. Had to open it up in a decompiler, strip the unneeded functions that Android decided to add, compile it, again decompile it into Smalley this time, which is actually like the Java bytecode for Android, strip it that way even more, recompile it, and then sign it, and then finally I got it down to 4.6 kilobytes. I was really impressed with myself. I thought it was awesome.
I was really impressed too, but unfortunately we still couldn't get 4.6 kilobytes reliably.
4.6 kilobytes.
So that was kind of a fail. It's worth further study. There are some people out there who have tried to tackle similar problems. You would think that there's some way. You have a shell on the other end of the serial port. We were like playing with shell functions to do integrity checking of a few bytes at a time, and I mean it was just nonsense. But we finally just moved on and investigated other ways to elevate privilege other than installing a payload as an APK. There's no wget in this shell, and this varies, of course, by the software build on the target device. But in most of the cases we're seeing, there's no wget, there's no netcat. Maybe we could like download data over DNS records, or like spam a bunch of SSIDs. I love that idea.
I tried. One of my potential attack vectors was because you could list SSIDs. I was just gonna like push out a bunch of SSIDs that were of some obscure length, figure out how to order them all, and use whatever very basic shell commands I had to recompile a binary based off of like base64 encoded SSID names or something. Like I was reaching. I was trying so hard, but we just could not figure it out.
There is a cool option that we didn't really pursue, but is worth investigating maybe for at least some target devices, and that's the fact that there's an ADB client installed on some newer phones that allows an ADB network connection. Mostly when we use ADB, we're talking to an ADB server on the phone to control the phone, but some phones have both an ADB client and an ADB server, and so there might be some way to, like, from that shell, activate an ADB client instance and do a remote ADB connection. Yeah,
you could actually like put something up in the cloud. Wow. This is Black Hat, isn't it? Sorry, no offense. So you could actually put up like an ADB service up on your own host, and then with ADB you have the capability of connecting remotely to a device on the network. This is used for like stuff like the Google TV, which you don't want to like sit at your TV with a giant long USB cable. You just open up a USB or a port on the network, and you can connect to it over TCP. That's awesome. ADB also has the ability to do push and pull. So this would allow us to take the device as a client, ADB connect up to our service, and then pull down files consistently. It just was a lot of work, and we found a better way.
Yeah, and a better way that's more universally supported. The ADB client thing might work, but you're only going to find it on newer devices and only on a subset of devices. You'll be really lucky to have that.
And then you also have to rely on network connectivity and a million other issues that just not worth it.
So you talk about this.
Yep. So the way that I figured it out was, there was no like figuring it out. I was reaching. I did it like an ls of the binary directory of Android and was just going through every single damn binary and figuring out exactly what it did. Like, oh, can I go out to a website? Oh, can I do file open on a URL or something? And I just couldn't find anything until I came around. I don't even know how I figured this out. I came around this binary called content, which in Android, the way that you access process or configuration settings in some way, and there are a lot of other Android smarter guys than I am, but there's a way you can access SQLite databases in Android that are shared across processes. So it's actually this content / settings. So that's actually a SQLite database that you're accessing. Secure is actually the table of that SQLite database that you're accessing. And you can do this from the command line. Now, generally, as a regular application, you would not have the permission to access this file or this database or any of that because non-privileged applications shouldn't be able to. However, it does, as a shell user, you actually are able to call this, even if you're, limited to just that, that GUID of logs. And it kind of looks like this, spits out a bunch of stuff, screensaver, accessibility display, Bluetooth stuff, some other random data there. And I don't remember, I was exploring it a little bit, trying to figure it out, and one of the settings that I saw was called ADB_enabled. So I just looked up the command line to actually trigger these flags. It was like a content update. It's actually basically SQL. Like you can just do a really rough form of SQL, and ADB enabled equals 1, and suddenly I get a kernel log saying ADB has been enabled. So the cool thing with that is now we have a reliable attack channel to actually connect to the device and do a million other things. We can push payloads, we can install applications, and we can have a lot of fun there. And
so let's try it. Let's do a little demo here.
Okay.
We're gonna switch back over.
Okay. If this crashes and burns, I apologize heavily.
So the goal here is to use our little home-built FTDI port with the connector, connect to the target device, get a shell using that FIQ debugger. From that shell, which is unprivileged, enable ADB, and then unplug the serial connection, plug back in with a regular USB connection, and use ADB to take over the device.
All right, so I'm hoping this is going to work. There was a recent change in Android that actually changed the location of this file to a table. I don't remember if I told you to surprise to account for multi-user mode. Yeah, so they changed it around a little bit, but I don't think I've updated this phone. So we're going to try it. So we can do ADB content query. Oh, oops. There you go. There you go. So this is actually querying with lots of freaking garbage. For some reason, if the screen turns off, it decides that it's going to dump kernel logs to the screen. I haven't really figured out why. As soon as you turn the screen on, it just stops. It's, special like that. Anyway, so lots of fun stuff, lock screen stuff, Bluetooth, screensaver, like you mentioned. I think screensaver refers to whatever that Dreamscape or something is called, recent stuff. So we'll go ahead and see if we cannot do. All right, so here we should be able to do settings, secure value of string 1 for whatever reason. It's a bool is a string in a SQLite database in Android because that makes sense, but we're ADB enabled. All right, now we get a little bit of spam out, and if we pray to the demo gods well enough.
Disconnecting the UART.
So plugging it directly into USB, not using the UART connection anymore, nor are we using serial. Make sure that I have it connected as a device. Cool. ADB devices. Sweet. So we're able to actually turn on ADB, and I'll disable it real quick because I realized I didn't show you guys it disabled to prove it. But we were able to enable ADB, and I don't have a whole lot of time to discuss all the things you can do with ADB, but it's pretty powerful. If you ever find ADB enabled on a device, you pretty much have unfettered access to it. You can unlock the phone. You can access all the contents.
Group permissions on there, right?
Oh yes, that's right. That's a good idea.
Yeah, because you saw earlier that he was the shell logged in to the console as a shell user with no group or shell group. There was only like one group that he was a member of. But now that he's in over ADB,
Yeah, now that we have ADB enabled, actually I just disabled it so that you can see that it's disabled. Sorry, re-enable it now. So now that we enable it, I'll show you all the different groups that we can do. Now, funny thing is the groups are fairly limiting. Without them, you can't do a whole lot of, I mean, you can't access the SD card, you can't access other data, you can't do a few different things there. However, you can update the SQLite databases. You can actually install and uninstall applications, which is why we were trying to push binary or applications over a serial connection, which was slow as hell and didn't work all that great. Oh, did I break it? I probably should have quit while I was ahead. And you can do all sorts of stuff. So once you actually have ADB enabled, it just makes things so much easier. I would ask you guys to check out a project I worked on last year called P2P ADB, which was actually just a fun little attack platform which would allow you to connect to a device that has ADB enabled. It would let you scrape tons of information off the device. If you had root enabled, you could do all sorts of neat little things. And in the end, like, you pretty much own the device in 5 different ways. You can install backdoors, you can install SSL certificates and configure, or CAs and configure proxies, and you can do all sorts of stuff. You can actually back up their whole phone to your drive, and lots of other little neat things there. Yeah.
Okay, so basically, ADB gives you total control over a phone at the same level of privilege as the owner of the phone. It doesn't give you root, just like the owner of the phone themselves may not have root. However, I have seen cases, I think only with custom ROMs on phones, I have seen cases where I logged into the FIQ debugger and typed console and was dropped right into a root shell. So it totally depends on the software installed on the phone, the particular model of the phone, and like Kyle mentioned, like a single model that you've heard of, such as the Galaxy S3, there may actually be a whole bunch of different model numbers that are called Galaxy S3, for example. So there are tons of different devices out there, tons of different hardware platforms. They all have different software builds. The software is changing all the time, and all of this affects whether or not we're able to use any particular attack technique. So it would be really nice if we had some way to probe these things automatically. Instead of having a fixed resistor that we plug in to the micro USB port, for example, and get a UART on it, it'd be nice to be able to connect variable with different resistors and try probing with for different protocols, including UART. There are a number of tools out there that we might use for this sort of thing, and the kinds of tools that I was thinking of were things like the Bus Pirate, the GoodFet, the Dot and Kraka, the new JTagulator. These all have some kind of similar characteristics in that they give you some way to connect to pins on a target device and manipulate them. However, they don't have all the features that we would need to do the kind of probing that we want to do. In particular, none of these solutions have a way to connect to or connect a configurable resistance between 2 pins. So I picked one of these. I said, well, the GoodFet is a project that I've been involved with for a while. I like the GoodFet, and I just happen to have my own GoodFet on the shelf that I've been playing with. This is the GFLPC 1343, which is kind of a mouthful, but it's a new variation of the GoodFet that I've designed, and it's it's just a little device that connects to your host computer over USB, and it gives you some connectors from which you can attach to target devices and do different things. When I first made this, and the first time I showed it to Travis a few months ago, Travis Goodspeed, the designer of the GoodFet, when I first showed it to him, I had visions of that scene in Return of the Jedi where Darth Vader says, "I see you have constructed a new lightsaber." But it's just my own take on Travis's design. And since it is my own take on Travis's design, and my company is Great Scott Gadgets, and it's a good FET project, I'm calling it the Great FET. And the concept of the Great FET is to take kind of what's good about the good FET and do something more with it. The good FET was my first surface mount technology board. Like the first time I ever did surface mount soldering was a good FET that Travis gave me. And one nice thing about the good FET design is that you can solder it up, plug it into a computer, and load code on it without needing any additional external hardware to program the thing. And that's really cool. And so one of the design goals for the Great FET is to continue that. It's a small board with not very many components, even though they're surface mount components. That may be something new for you if you've never soldered them before. It's something that's accessible for like your first time SMT soldering project, and you don't have to have another board to like bootstrap the process of loading code on it. You can just solder it up, plug it into USB, and it automatically starts up with a USB bootloader for you to write code for it. It's lower cost than the existing good FET designs. Travis designed the good FET originally around microcontrollers from Texas Instruments that he was able to get free samples of. So it's a great design for people who want to build just one, because Texas Instruments will send you a free sample of that one expensive part. But it's an expensive part if we were to, anyone who's tried to manufacture good FETs in volume has found that that integrated circuit, that microcontroller, is really needlessly expensive. So I wanted to get a lower cost microcontroller on there. I wanted to have more pins available for connecting to target devices, and I wanted to have the ability to connect small expansion boards. So instead of having a good FET and a face dancer, for example, which is kind of a variant of the good FET, and all these other variants of the good FET that we've had, it'd be nice to have one great FET and then like a front end board, a little small expansion board that's just the face dancer add-on, a little small expansion board that's a radio add-on for certain functions. And so I decided to make a small expansion board that would be an add-on for the Great FET for this project, something that would connect between the Great FET and the phone or the tablet we're connecting to. So this is the small expansion board next to the Great FET. It ended up not being so small. There's like 200 to 300 components on that board. It became an incredibly difficult design project that took me months longer than I anticipated. And it's sitting here on the table. It's not huge, but it's a lot bigger than the Great FET. It's a lot bigger than I originally intended. And how did this happen? I call it Toad. It's the totally over-engineered adapter detector, and it's a ninja toad. I just wanted to call something Toad because toads are ninja. There's actually, if you're not familiar with the tradition of ninja toads, there's actually like this whole history of toad magic in this tradition in Japan. So this is like an old 19th century print or something. But anyway, it's Toad, and the goals for this project were, first of all, to be able to plug into a target device and implement a UART to talk to it. Now, I wanted that UART to run over arbitrary voltage levels. Like some devices talk at 5 volts digital, like 0 to 5 volts. Some talk at 3.3 volts. Some talk at 1.8 volts. Some of the newer phones want to talk to you at 1.2 volts, and it's just like a downward trend. The Galaxy Nexus we were demoing earlier actually wants to talk at 5 volts. So it's very important to support all of these different voltage ranges from at least 1.2 volts to 5 volts. But making it work with arbitrary voltages makes it a little more complicated. I also want to support non-UART stuff. There may be interfaces on these target devices that are arbitrary digital interfaces that would be nice to interface with. I definitely need to be able to connect a configurable resistance within a fairly wide range of resistances between any 2 pins on the target device to be able to try to activate that accessory detection. I want to have an analog to digital converter on here that I can connect to any 1 pin and measure the voltage on and see what's going on for probing these things automatically. I want to have an arbitrary pinout So I don't necessarily, maybe I know the target device has a UART, or I think it does, but I'm not sure like which pin is transmit and which is receive and which is ground. And it'd be nice to just be able to automatically probe and find that out and connect my UART to any pins. It turns out if I do have an arbitrary pin out, then I have to kind of like guess which one is ground, and then the other pins I might have guessed wrong, and so I might have some negative voltages show up. So I had to design the board to allow for negative voltages, which makes it a lot more complicated. And then I thought, well, hey, if I'm supporting negative voltages anyway, why don't I implement RS-232 levels? Because that uses these big plus and minus voltages. I'm going to have a negative rail and a positive rail anyway. Why don't I just make them big rails so I can support like up to plus or minus 15 volts? And now I have a universal serial adapter that can talk RS-232 or UART, or TTL UART on with any voltage level I want, and with arbitrary pinout. This all seemed really cool, but it made the project become ridiculous and complicated. And I just finally soldered this board together last week, and it doesn't work. So,
Oops.
So, however, it is a work in progress that is open source. It's open source hardware. It's open source software. It's in the GoodFET repository. So, if you go to the GoodFET repository, you can find both of these guys, the GFLPC 1343, which I'm now calling the Great FET, and the Toad. Both those designs are in the repository. So if you're an open hardware guy, if you're interested in these kinds of things, if you're somebody who wants to experiment with these attack surfaces, I would love to talk to you and work with you on trying to make this thing work so that we can do automated probing of these interesting attack surfaces that so far we've only been probing manually and slowly.
So I do find it really funny. Part of the goal for him trying to build this sort of device is so we didn't have to have this really stupid, dumb, bulky, annoying thing to carry around, and wanted it to be just as small or comparable size to this hastily put together little thing. And Now Samsung doesn't look as stupid as we thought they originally were.
Yeah.
But at least it's programmable.
That's true.
It's not.
That's true. We don't have dip switches to flip every time we want to change a setting, at least.
So we know that other manufacturers use this. We were picking on Samsung because it's the easiest. We know that the LG has kind of a similar deal with the Nexus 4. You can, I want to say it's JDuck that found it. You would know, wouldn't you, Jesse? No. I think it's JDuck that found it. He had put it on the AccuBomb blog. You could take a specially designed audio jack and put it into the audio jack, and you can get serial data. In older phones, I mean, this has been around for a long time. In old phones, like the dumb phones, Nokia Bricks or whatever, they had the same sort of deal because they didn't want to have like pin outs. They didn't want to have like tons of extra components. They would just combine them together, and then that's how you would program the phone. And now there's a whole lot of implications for that. I mean, the most obvious attack vector for something like this is if you're going through, say, TSA or customs, or you get pulled over, or someone is, for whatever reason, has access to your phone and you don't want them to get into there, and you think you're fine because you have a lock screen, ADB disabled, and all this other stuff, they, can just plug in this device and access shell in some instances and bypass all of these features. And I've looked hard. I haven't seen any forensics tools that actually use these sort of devices. I'm sure they exist. Well, I would hope they exist based on how much they charge for some of their tools. But I hope that they're doing some research. Actually, no, I take that back. I don't hope that they're doing research, because that means that these sort of things could already be happening to people. Yeah. It is something to think about that, even if you have all those protection enabled, you could bypass it because of these more or less debug backdoors that aren't really known to exist.
you know?
Yeah.
So we first presented some of this stuff at Infiltrate. So this URL is still there. A lot of our materials related to this project are at that URL. I'm going to add a few more there, like our Black Hat white paper, which has some more details, and some of the newer links to some of the newer stuff we've been doing. And I think we have 30 seconds or something for a question if somebody's quick. Anyone? Questions?
I
No?
did want to type ID again just to show it. So we went
Oh
from,
yeah, there it is.
We
All
went
those
from,
privileges.
I'm in a VM, so things suck and take a while to connect to the VM over USB or something. But we went from UID is 2000 shell with just group ID of log to now we have shell graphics input, mount, ADB, SD card, which will let us read and write to the SD card and all that. And that's from enabling ADB from this input.
Right.
Because of that, you can also do ADB install, ADB remove, and all that sort of stuff,
Right.
and disable lock screen.
Let's take one question.
What proportion of the devices you tested were you actually able to activate ADB?
We, in my possession, I was only ever able to get shell on devices that were modded, or had custom ROMs on them.
I found I've been just kind of randomly saying when I've been hanging out with somebody, I'll say, "Hey, can I plug something random into your phone?" And I've found a few, maybe 20% of the phones that are a model that I know how to access UART on. Maybe 20% of those that have carrier installed OSs have actually given me access to be able to do this.
I've tried, I've bought a bunch of, there's some other stuff in there, but I bought 10 phones on eBay, all from Samsung, just to try to find phones, but they're all different. They all have different expectations of it, and the S4 is different than the S3, which is different than the Galaxy Nexus, which is different than all the other ones.
Right.
And it's impossible. Well, it's going to take a long time to document all this stuff if
Right.
we have to sit there flipping dip switches all day long.
And there are some where you can connect over a USB port. There are some where you can connect over a headphone jack. There may be others that are other types of ports that we haven't even seen yet. Who knows?
Yeah.
So anyway, we think this is cool stuff, new attack surfaces. We hope you like it. Thanks for coming.